This episode is sponsored by Brilliant. Every year, hundreds of elves are tragically injured in toy manufacturing-related accidents, while reindeer are driven to the brink of exhaustion. But in the future, they may be replaced by robotic factories and delivery drones. So today's episode comes out in the midst of the holiday season. And of course, many wintertime holidays have a bit of a focus on gifts and good cheer, which I've often suspected was meant to help counteract the rather glum mood that comes with the cold and snowy time of the year. Of course, the most familiar avatar of gift-giving is Santa Claus, so it's no surprise that one of the common terms for hypothetical devices that can make almost anything is a Santa Claus machine. One of the most well-known fictional examples of that being the replicators in Star Trek, which can produce many things by a simple verbal command, notably tea, Earl Grey, hot. These are also often known as Cornucopia Machines, for the Horn of Plenty, and if we'd been doing this episode around Thanksgiving, we'd probably have titled it that, but it's December, so Santa it is. As a young and rather credulous kid, I once asked my grandfather why Santa was at the North Pole, and in an impressive display of ad hoc composition, he said it was because there was a large supply of minerals and oil in the Arctic regions, and Santa needs a lot of raw materials to make presents. There was no Google or Siri back in those days, so he was fairly used to fielding bizarre questions from me, and I suspect breathed a sigh of relief when my sister finally taught me to read. But it got me thinking on the logistics of Santa's annual gift-giving operation, and I tended to revisit the topic every Christmas as I learned more math and science, and grew increasingly shocked at the sheer scale that would be necessary. In hindsight, I'm not sure why I didn't just go look up the statistics of the Christmas industry, which, if you're curious, in the US alone is a $500 billion annual industry, estimated to involve almost 5 million jobs at home and abroad. Now, the assumption that this means 5 million of our proverbial elves working in megafactories at the North Pole would be incorrect. Most would be in other aspects of the manufacturing and delivery process. Tens of thousands of elves doubtless work on Arctic oil rigs or warehouses, and some presumably have the unpleasant task of cleaning the reindeer stables. How many work in the vast polar foundries and factories would depend on the degree of automation involved. And ideally, almost all of these processes could be automated. This of course takes us into our topic for today. Machines able to produce anything in fiction generally tend to appear to do so almost like a magic wand. It just appears or fades in, likely simply as a time saver for special effects and props departments who can just pause the recording and stick the item into the shot. However, such a machine need not be arcane and compact, but more likely a very large automated factory, at least initially. There are many hypothetical and fictional examples of entirely automated manufacturing, but the most likely is what we call a clanking replicator, an artificial self-replicating system that relies on conventional large-scale technology and automation rather than nanotechnology or teleportation. Think of a large automated factory that was able to deploy robots to gather raw materials and could turn those into every device needed to operate that factory, including those robots, who presumably also do the assembly. Non-artificial examples of a clanking self-replicator include humans, and really any organism, indeed all our cells. A typical cell, while microscopic, is less of a simple machine or factory than a giant city full of warehouses, refineries, factories, roads, and distribution networks. Evolution has created a dizzying complexity in each cell by trial and error without the need for a brain. Each cell is a self-contained, self-replicating survival machine. We can assume it will be possible at some point for us to make our own artificial ones, even if we have to piggyback on existing biological cellular structures to do this. For that reason, while many of the devices we'll discuss today are more speculative and iffy, the clanking replicator itself is considered an inevitability, a matter of when, not if. The other more classic example in sci-fi is tiny little nanorobots able to reproduce and perform tasks, which raises the doomsday scenario of what's called gray goo, which is when they run loose and turn a whole planet into more of themselves. This is also likely possible if we were just discussing cells, since cells are microscopic and so are viruses, which are even smaller and essentially a working example of gray goo. Indeed, you could argue our planet has already been gray gooed, or maybe green gooed. We just happen to be the end result of that. Much smaller ones, able to manipulate individual molecules or even atoms, are called universal assemblers, and their feasibility is a bit less certain. Eric Drexler, the gentleman who got the debate started in earnest with his 1986 book Engines of Creation, offers us one example called a molecular assembler, ultra-tiny machines able to take individual molecules and build anything, including more of themselves from them. About the same time we got our hands on buckyballs, a new carbon allotrope that opened the doors to carbon nanotubes, graphene, and serious discussion of nanotechnology. The inventor there was Richard Smalley, a chemist who was born just down the road from me in Akron, and would later receive the Nobel Prize in Chemistry for the discovery. He and Drexler got into a debate about the viability of such machines, now known as the Drexler-Smalley debate, a series of articles and open letters the two exchanged in the early 2000s. The debate isn't about the possibility of manipulating molecules or even individual atoms. Specialized proteins called enzymes in all biological cells and even viruses manipulate molecules all the time. We've also had industrial solutions since the 1980s that can manipulate individual atoms using scanning tunneling microscopes. The debate rather centered around whether we can miniaturize these types of machines and make them self-replicating. Both Drexler and Smalley raised many good points, but of course the key one from Drexler is the notion that you should be able to make something very tiny able to reproduce itself at least a couple times before breaking down, leading to an exponential growth process, same as we'd see from bacteria in a petri dish. We can't be sure yet what that minimum size can be, but can use biology as a safe upper maximum. One of the points raised by Smalley, though, is of special interest to us today, as is the basic concept which can be expanded to other types of these machines. This is the sticky fingers problem, sometimes also called the fat fingers problem. Any machine is going to need some sort of finger equivalent to interact with whatever media they are in and to build stuff. These have to be made of atoms and thus have an irreducible size. I can use my hands and fingers to handle large objects easily, but need special small tools like tweezers to work on anything smaller. To quote Smalley, because the fingers of a manipulator arm must themselves be made out of atoms, they have a certain irreducible size. There just isn't enough room in the nanometer size reaction region to accommodate all the fingers of all the manipulators necessary to have complete control of the chemistry. Also, the atoms of the manipulator hands will adhere to the atom that is being moved, so it will often be impossible to release this minuscule building block in precisely the right spot. Both of these problems are fundamental, and neither can be avoided. Self-replicating mechanical nanobots are simply not possible in our world. Needless to say, even if this argument is true, it does not rule out self-replicators, just ultra-tiny ones. Again, biology offers billions of different schematics of functioning microscopic ones. Nor do you necessarily need precision placement on atoms to get them in the right place. Time will tell on those, but the problem shows up when we discuss 3D printing. In 3D printing, you are layering a substance, or a few different substances to create an end product. The higher your resolution, the smaller your printer heads or nozzles need to be, or the more numerous. As with the fat fingers problem, while we could assemble a vast two-dimensional array of nozzles, those nozzles still must be bigger than whatever is coming out of them, even if we assumed a single material, not multiple substances with their own nozzles. So the nozzle array does need to move back and forth or side to side to print a layer, just not a lot. Way back in the self-replicating machines episode, I mentioned that there is a maximum speed you can print at an atomic or molecular resolution. We probably didn't spend enough time then to clarify some objections, but we've got some speed limits on this. Firstly, you obviously cannot use just a few nozzles, one for each substance, as trying to print out anything, even microscopic, with atomic detail on any sane timeline would require the needle to move so fast it would generate sonic booms and tear itself apart. Anything macroscopic would require it to move at relativistic or even FTL speeds, and require the kind of super strong materials only found in science fiction. Santa's toys are going to be blown apart and end up a useless wreck. Here's our second speed limit. Printing at this resolution, the atomic or molecular level, means anything macroscopic has on an order of 1 billion layers. So even if you have many nozzles, they all have to be moving in unison, each with its own area of coverage. Only materials don't actually move in some perfectly rigid fashion, they compress and wave. A common thought on faster-than-light travel is why you couldn't have a very long and rigid stick from Earth to Mars and just push on it on Earth and poke someone on Mars instantly. This doesn't work, and indeed they'd not get shoved by the end for years because you didn't push on the stick. You pushed on a package of atoms near one end, which then push on the next set closest to them, who do the same and so on, sending a wave that is moving the stick and doing so at typically a few times the speed of sound, depending on the material. The short form is you can't just shove on some big printing nozzle array and expect every last nozzle to move instantly the exact right distance to the sub-nanometer scale and disgorge their next bits or pixels on the right trajectory, then a nanosecond later gets shoved again and repeat. So you can only go so fast and maintain accurate resolution, and such a device is pointless if it isn't accurate. I don't need to 3D print a concrete house at molecular resolution after all, and thus can move faster. Now you could angle the nozzles like pivoting cannons, each shooting at their own area, though it's always worth remembering that you need some machinery for that kind of thing, and that takes up space, and the more area each has to cover, the faster it needs to spin and stop. And as an example, a kilometer-long railgun on a spaceship cannot pivot and shoot at a new spot in an instant, because turning that fast would rip the gun right off its mountings or snap the barrel from centrifugal force. None of these nozzles are being made out of unobtainium. They have to obey real laws of materials, acceleration, stress, relaxation times, inertia, and at this scale, quantum mechanics. If you can get through all of that, you still have another speed limit, which is how fast your ink is moving. If you're throwing colored balls at the wall to stick and form a pattern, you can only throw those so fast before they'd start bouncing off, or smashing themselves and the wall to bits. You can't throw atoms and molecules around to hit each other at supersonic speeds, let alone relativistic ones. When those atoms land on the previous layer, they had to be moving slow enough to get caught and not damage the connections of their neighboring atoms. Nor can you spit out new volleys right behind them, which leave before the previous one landed, or you'll start getting lots of interactions between the particles as they approach. And if you're thinking you could get around this with extreme precision calculations, don't forget quantum, because we are doing this at the scale where something's momentum and position starts getting uncertain. And remember, any extra energy of motion of those particles is turning into heat. Printing circuit boards at the atomic scale is probably doable. Printing a cup of tea in a few seconds is probably impossible. One hates to imagine the sheer amount of computation that would be needed to rapidly print any macroscopic object in a few seconds without everything getting jumbled up, but it would probably slag the device, and possibly the city it was located in, from all the heat generated running the math. We've another example of making tea besides Star Trek. In The Hitchhiker's Guide to the Galaxy, Arthur Dent ties up the whole computer in a quest to synthesize a proper cup of tea, and it's not hard to imagine why. Any macroscopic object contains trillions of atoms, each of which would need to be precision placed. Of course, the classic Picard Star Trek menu option of Earl Grey presumably relies on transporters to teleport stuff into place. In theory, you might be able to use quantum entanglement to copy an existing cup of tea onto a pocket of matter, but since the no cloning theorem would wreck your template teacup and entangling trillions of atoms together just to make a cup of tea seems fairly ludicrous, we can probably discount that approach to teleportation replication in the future, and it is our best option for making teleportation technology under known science. See the teleportation episode for details. One last major concern, which may be an even bigger problem, is heat building up in whatever you're printing. After all, on atomic or molecular scales, heat and motion are the same thing. This is something we discussed back in the nanomachines episode, but it is definitely worth bringing up again since it's one of the biggest problems with molecular assemblers. The amount of heat that can be rejected from a given volume is directly related to the amount of surface area and how conductive that material is. The smaller you go, the less surface area. So if you're trying to print too quickly, you'll end up melting whatever you're trying to make, and possibly the machine trying to make it too. This might be an option for making self-cooking food, but proteins aren't the strongest of structures, so even there you could destroy what you're trying to make before it's done. Santa's Christmas mince pies are going to end up a lump of smoldering charcoal. Come to think of it, isn't it convenient that those on the naughty list get a lump of coal? Maybe Santa's been experimenting with a Santa Claus machine for some time. Of course, all of this only matters if you're aiming for resolution at the atomic level. Your feedstock material and nozzles can all act a lot faster if they're printing at a lower resolution like the microscopic. A cellular printer, as opposed to an atomic one, is using as its bits or pixels individual biological cells, and each of those contains trillions of atoms. The problem is, as what makes atomic printers more tempting, is there's a lot of different cells, and you pretty much need a nozzle for each type. An atomic printer only needs a maximum of around 100, since that's how many atom types we have, and typically you would only be using a handful of types. A molecular printer is much worse. This brings up the issue of specialized manufacturing, which is exactly what these sorts of universal assemblers are supposed to circumvent, a general or universal creator of objects from some data template. A specialized food printer, for instance, could just have nozzles for protein, fat, and carbohydrates. That's what most of food is, with just some trace micronutrient vitamins. Of course it is not. Most food is mostly water, but that at least is very standardized. There's only one type of water, ignoring various isotopes that mostly don't matter chemically. That's not true of carbs, fat, and proteins. Even ignoring that proteins are size-wise to a carbohydrate what a skyscraper is to a hut, they all come in a lot of different types. Even amino acids, which proteins are made of, come in many forms, even just limiting ourselves to the main ones in biochemistry. For carbs, you've got monosaccharides and disaccharides, the most commonly recognized being glucose, fructose, sucrose, and lactose. They are, in turn, built into polysaccharides, made of a dizzying array of combinations of these. Polysaccharide examples are cellulose, which paper is made from, and starches, like you find in your potato chips. We also don't eat most of our food raw, and it's kind of hard to print a loaf of bread from a big dough vat. You might be able to make a machine that can print any food on demand, maybe even on a same timescale, but someone is bound to point out that a centralized facility, or facilities, can make this better and faster and deliver them to you by drone in many cases. You could also employ a swarm of drones, each with specialized tasks, hanging around till they get a call. The notion that building a ton of drones might take a lot of effort comes to mind, but can be instantly discarded, since you are specifically talking about machines that make stuff. You're not building 10 million specialized drones for making or delivering a certain class of item. You are building one machine that makes those drones, or makes the machines that make those drones. When I was a kid, the big new rage was Domino's promise to have pizza at your door in 30 minutes or less, or it was free. Nowadays, we're seeing this get expedited with the notion of devices which bake the pizza en route. It's an alternative scenario for Santa too, that instead of having some Doctor Who big around the inside sled that can store vast amounts of matter in TARDIS or Hammer space, or reindeer able to move at faster than light speeds to return to the North Pole for loading whenever the cart runs dry, that Santa's sleigh is a matter replicator ramjet that sucks in air as it goes and subjects it to a lot of chemistry and transmutation to create gifts. This is complete with nanoscopic elves inside doing the work. Gotta have elves, of course. I've no idea where they get the energy for this, but I have long suspected that Rudolph's glowing red nose actually indicated a radioactive atomic power source was mounted there, or perhaps a Kugelblitz black hole. While this would explain how they obtained the necessary speeds required for the trip, and possibly the time dilation implied, I still have not determined what purpose the cookies serve in Santa's refueling operations. It would seem to imply thus far unknown properties of chocolate chips as an energy source. Further experimentation is probably advised. Now, assuming you get one of these replicator methods working, even just the clanking replicator, we have the issue of unemployed elves and reindeer to deal with, and of course people, already an ongoing problem as technology improves. Something like this is likely to develop gradually, and as we've noted before, a surplus of cheap goods tends to largely address the issue of getting paid so you can buy them. However, what replicators, self-replicators in particular, introduce is a new paradigm of manufacture. It's the complexity more than the size or quantity that is your bottleneck. It's weird to think of some vast cylinder space station hull massing gigatons being cheaper than a single thumb-sized microchip, but as long as you've got quadrillions of tons of raw material lying around the solar system, it's really the design phase that's expensive, not the production itself, and a big hollow metal cylinder is not exactly complicated. In theory, you release a single clanking replicator whose additional product is sheet metal on an asteroid, and check back in a few months later, job complete. It's not really going to tie up hundreds of R&D teams to program and modify it to take in rocks, smelt them, roll them as sheets, and weld them together, whereas you might need hundreds of people to design the printing template for a single dessert item, or a single microchip, or just one door in an airlock on that cylinder hab. We'll discuss this more next week, when we look at using this kind of technology in place of giant generation spaceships, but it's a thing to remember, even nowadays thought and complexity are way more expensive than raw materials or labor. A freeway is much cheaper, pound for pound, than microchips, let alone the weight of a thumb drive holding the schematics. Data itself doesn't really have mass, whereas it obviously has a vast value. The various templates designed for replicators, be it 3D printers or nanomachine assemblers or Trek-style ones, are likely to be hugely valuable and a major industry. Indeed, maybe one of the few industries left if devices like these are developed. One can imagine the kinds of funds and feuds involved in intellectual property rights in this regard, from copyright lawsuits to piracy. Now, the piracy issue mostly would be a problem if everybody had a Santa Claus machine in their basement. As we're seeing today, it would most likely instead be a lot of somewhat specialized printers at depots with delivery by drones or mobile printers that got an order and headed your way while making it. However, if we did have them so everyone could have one in their basement, that intellectual property rights issue is secondary to the terrorism one. Forget printing a nuclear bomb in your basement from a pirated template or some anarchist cookbook online. You'd have problems getting the uranium unless your Santa Claus machine had cheap transmutation too, in which case you'd probably make antimatter bombs instead. Rather, you have to worry about any random lunatic printing up a lot of ricin, or hunter-seeker killer drones, or worse, self-replicating hunter-seeker kill drones. I did mention this was the nightmare before Christmas, didn't I? This sometimes gets suggested as a Fermi paradox solution, and is one of our examples of suicide-pact technologies, ones where everybody inevitably invents it without realizing it will wipe you out, or where it's just so attractive or easy that it ends up happening even though you know it's dangerous. It's not always in an obvious way either. We see an interesting example of a civilization collapsing and rebuilding after it gets its hands on a cornucopia machine in Charles Stross's novel Singularity Sky, where everything falls apart simply because nobody needs anyone else at all, and we explored some of the consequences of that in our Post-Scarcity Civilization series in more detail. Great book, by the way, deals with a lot of issues of extreme and godlike artificial intelligence and technological singularities too. We often classify artificial intelligence as another possible example of a suicide pact technology, and it indicates another possible weird scenario in this case. We probably don't have to worry about the prior example because, as mentioned, these are unlikely to be something everyone has in their basement, but rather lots of slightly specialized ones working from central depots for drone delivery. Amazon dialed up to 11, basically. Such a scenario makes it way easier to control it against dangerous tech and copyright violations because only certain people can approve new templates, and it won't print anything not on that template. And people don't go up and fiddle with it either. Drones fly in and pick up goods for delivery. That's not completely secure, of course, but better than any lone random lunatic being able to bring about the apocalypse in their basement. However, any given template will need some customizable parameters. I don't want a shirt. I want a shirt of a specific material, color, size, shape, etc. One problem we have now with online shopping is that you've got millions of products, and usually at least many thousand that would show up for any common keyword that you need to sort through. In many cases, a lot will be standardized to the person though. I don't need to see every type of tile or seat cover available, just the ones that will fit my car's make and model, and you can enter those, so whenever you search, it only offers you the ones that fit that. Similarly, you can obviously select clothing sizes while shopping, but even these are fairly general compared to tailoring, and it would be nice if your phone just scanned you regularly and kept your measurements updated when you went clothes shopping. However, it's not just if it fits, but if it looks good, and that's not only more complicated, but something we often want a second opinion on, not just ours. So a computer can't just take our scan and CGI a model of us in that garment to see if we like it. I mentioned in the episode Jobs of the Future that consulting would be a big industry in the future, and often for surprising things. But it's easy to imagine one of the earlier uses of AI would be using it to help pick out the right clothing fashions for people. We always worry about AI going crazy on us, either Skynet-style defense computers or some grey goo like the paperclip optimizer, but there may be more mundane and less threatening routes. Imagine instead an AI built to advise people on fashion, maybe one with an Asimovian prescription about harming people with insults when it tells them that they really do look fat in that garment. Consider also that people are bound to use it for some opinions on some fairly bizarre clothing since they can do it in private. That's a big market requiring endless banks of supercomputers trying to handle the often illogical fashion tastes of billions of people, and probably not monitored as closely as a defense computer would be. I could so easily imagine that fashion computer going quietly, utterly, and homicidally insane. It reminds me of the robot Santa Claus from Futurama, which, due to a programming error, had much too high standards for who was naughty and nice and how to deal with that, and went mad and flew around each Christmas attacking people. Devices like the ones we've looked at today offer us a future where almost anything we could wish for was ours for the asking, just like a genie in a lamp. And just like that, it is always good to remember to be careful what you wish for. While a Santa Claus machine can make almost any object you might wish to gift someone, the one thing it can't give them is knowledge. Knowledge, as we all know, is priceless, and a love of it is the gift that keeps on giving. Help your loved ones nurture their curiosity and build problem-solving skills in a fun, bite-sized way with Brilliant. Go to brilliant.org/IsaacArthur and grab a gift subscription to spark a lifelong love of learning. So we looked at replicating machines today, and next week we will close out our 4th year here at SFIA with a look at how this technology might help us colonizing the galaxy in Seeding the Stars. And while that will finish us out for the year, SFIA will be back the next week to start 2019 up by examining a different sort of travel to different sorts of worlds as we take another look at virtual worlds, simulated realities, and how they might become very real indeed. For alerts when those and other episodes come out, make sure to subscribe to the channel and hit the notifications bell. And if you enjoyed this episode and haven't bankrupted yourself shopping for presents, we'd appreciate your support on Patreon. And if you have, you can always hit the like button or share the episode with others. Until next time, thanks for watching and happy holidays.